Hello and welcome back to Stationeers. I'm Mick and we're back in our Mars base here and we're going to do a little bit of coding today. So it's time for a really difficult one. We're going to talk about bit mapping and bit masking. So make sure you've got on your nerdiest underpants because this one's going to hurt your brain. Now what is bit mapping? Bit mapping, it's about binary bits. The bits in binary, well, binary is the language that the computers work with. So as humans, as stupid squishy humans, we use a base 10 numbering system there, presumably because we got 10 fingers and I don't know, but that's why. Well, actually, the ancient Babylonians used a base 60 numbering system. So instead of having the numbers through different digits for sort of 0 through 9 like we've got, they had 60 different digits. I can't imagine why they didn't use that anymore. But I mean, it's what it is. I mean, the old early computers used to use a binary, try and use a decimal numbering system as well. But the computers had to represent the numbers by different voltages. And if it's between two certain voltages there, it's a 4. If it's a little bit higher voltage, it's a 5. But it was difficult to maintain the voltages and know exactly what was right there. So in the end, they decided, right, stuff it. We're not going to do a decimal numbering system. We're going to switch to binary. So the numbers can either be a 1 or a 0, and that's it. So the circuit is either on or off, and that's all it is. So there's less confusion. That makes computers more precise, but it's just that people don't think that way because we're used to decimal numbers. So deci, of course, meaning 10. So we work with numbers 0 through to 9, just 10 different digits. Once you get to 10, you move over to the next column there and increase the order of magnitude. Well, binary is it's not the same, but it's a similar thing where it only has 2 states, which is a 0 or a 1. So once you get to 1, you want to add another number to it. There is no number 2, so you have to increase your order of magnitude, and it goes to 0 or 1, 0, sort of what we'd call 10 if we were using a decimal system, but in binary it's 2. And of course when you add 1 to that one, it becomes 1, 1, and there is no 2. So if you add another one to that, it becomes 1, 0, 0, which is 4. So you've got to kind of get your head around that to make things work. But it's not the silliest numbering system there. I mean, imagine if your numbering system changed with each order of magnitude. How could a society ever function with that? Now, we have done a bit on data encoding before as some of the previous videos there, but we've got this time we're focusing on binary. Why are we focusing on binary? Because we have, well, a fair while ago now, we've been given the devices that have internal stacks. And to be able to use them, you have to be able to write to the stack. And a lot of the stuff we have there requires multiple values to be written and encoded as a single value. So if we look at this one here, it's it's electronics printer, it's up there somewhere. We have these instructions here. So we're working on a 64-bit value which is passed to the stack. The first 8 bits are going to be a value which is the operation code, in this case 1, and the next 20. Nice counting. The next 16 bits are the index, which is just a value we give them as well. So we're coding them together into a single value, which contains 2 values. How do we do that? Well, they have given us a few handy operators there when this came out. They gave us a few operators there to actually work with these. So this one requires 3 values to execute recipe, which is the operation code, which is 2 to tell it that you're executing a recipe, the quantity, how many of them you want, and the prefab hash of what you want to print that many of. But then you have other ones here, like your missing reagent function here. It comes down to the end. It has returning information to you. So it's returning a coded value to you with 3 values in it, and you have to be able to extract those 3 values in order to use them. So what are we going to do about that? So what we have got is the shift, left and right functions. What well, let's start trying constructing something, I guess. All right, so we have some code here, very basic. There's no loop here. We're just putting the value of 1 into R0 and displaying it on the D1, which is the display. And if I export that, surprise, surprise, the display shows 1. Now we can put in here, let's say we have our bit shifting values. So 1 is 0, well, 0, 1. If we can then bit shift that 1, move it across. So if we shift left logically, we have a couple of ones. You can shift left or right. We want to shift it to the left because I do. Logically means all the new digits that appear at the left are zeros. So that will make sure that the 0, 1 that we have will become a 1, 0. So if we shift logically left, R0 will take the old R0 and shift logically left by 1 digit. So it should become a binary 1, 0, which is 2. Export, it jumps to 2. Of course, we shift it logically left a further 1. We shift it by 2 places. It'll be 1, 0, 0, which should be a 4. Okay, so we are then, so we're creating a value there. So if we look at what we want for something there, let's just put in anything. Let's say we want to execute a recipe. We want to put 3 things in there. So we need the prefab hash of what we want to put in. We need the quantity and the operation code, which is a 2 for that. So prefab hash is easy. We can just pick whatever we want to prefab hash. All right, so if we want to take glass sheets, so if we want to print them, we'll copy them, and we should put that into our value there, paste, and let's just get rid of that one for the moment. If we confirm that, export that, and well, that is the number we put in there. If you look at our tooltip there, that is the number we put in there. It's too long to show on there, but it is the right number. Now, if we check our printer thing, okay, if we come back to here, we find that the prefab hash, we want that in bits 16 to 47. So we've got to sort of shove that across by 16 bits. So that is just a matter of shifting it logically left by 16 bits. So we shift logically left by 16 bits and confirm, export that. It is now a completely different number. The number we're passing there doesn't really matter because it is a coded value. The pattern of the bits that were there for the previous one are still the same. They've just been shifted over 16 positions. Now, the other things we needed in there were the operation code, which is 2, and the quantity, which is, well, let's anything, 5. Edit. So we shall want to say move into R1, which was a quantity. Why am I doing that one next? I don't know. Why not? Was the quantity, we wanted to say 5 of them, and so from here the quantity had to be in bits 8 to 15, so we want to shift that one left by 15 followed by 8 bits. So I shall shift logically left R1 by 8 bits, and the final one was the opcode. So that's going to be opcode 2, which is just the value from, well, we want that in bit 0, so that is just straight 1. I wasn't straight 2, I was close. So we move into R3, the opcode, or R2, the opcode, which was 2. So they're the 3 values we need. Now we've got to combine them. Now, because they have all been set up and matched so that none of the bits should be conflicting with each other, we can just add them all together. Now, we have been given a number of commands there which will allow us to combine. We do have bitwise commands such as OR and probably some others which I can't think of off the top of my head. So we want to look at them, but we can just add them together because we know that they're not going to overwrite anything there. So just adding them together will work fine. So we add R0, R0, R1, and we add R0, R0, and R2 and show that the result there now. So if we export that, okay, the digits were that far below you didn't even see them there, but they have changed. So we've added those into there, and that is now a 64-bit value that contains the 3 values we need to send to the printer, which is not going to listen to me because it's on the floor over there. But that's how we've joined them together. Okay, so that is a way you can do it. Typically when I've been doing it, I just build the command as I go along. So if the wrong button, if you look at what we need, is you need the prefab hash, then you need the quantity next to it, the next 8 bits, and the opcode in the last 8 bits. So what I would normally do is put in our prefab hash, which we need, move that across 8 bits, and then we're ready to add in the next one there. So all we then do is add R0, R0, and the opcode, which was, the quantity. The quantity we wanted in there was 5. So let's get rid of all that stuff. So we take this code, we move it across by 8, because the next value is 8 bits wide, and then just add the next value in. Then I can move it across again by another 8 bits to make room for the opcode. So we shift logically left R0, R0 by 8 once again, and we add R0, R0 in the opcode, which was 2. Confirm, yep, see, our opcode is 2. So that is just another way of building it all. So we start from the high end and just shift it across 8 bits, add in the next one, shift across another 8 bits, depending on what it is, of course, because some of them will be different if we, I don't have an example of that at the moment, but there you go. Yeah, they're all 8 bits. Okay, so that doesn't really do well for a demonstration. But that's how we're building the code. So we've got 3 different values, all just connected in, joined into a single value, but it is the pattern of the bits in there that is important, not the actual number at the end. As long as we preserve those bits, we're fine. Which now brings us to the bit of we can build those values easy enough, send them off to the stack, but what happens when we get some back? With printers there, if it's missing some reagents, it'll send back information to you, which is the opcode, the quantity that it needs, and the type of material that it needs. And it'll be a single value, and now we have to pull that apart to get what we need. So that brings us up to bit masking. So as we can actually apply a mask over a certain bit of it to filter out just the bit of information we want, so then we can then shift it back and have a look at the number. So we shall build, we've actually got something like that, reagent. Well, we'll pretend what we've got there is that. So we've got this value here, and we shall now disassemble it back to what we've got. Now for this we need our logic operators, which we have there, which are going to be AND. Now you have to be careful with AND. Just as a side note, we have to be very careful when we use AND in any of our logic operations, because AND is a bitwise operator. So if we look at U, so if we look at U, and we find performs a bitwise logical AND operation. So it will not just look to see if it's 0 or non-zero, it will check each bit within the number to find out whether or not it's true. So what we mean by that, two dials. So they're both set to 0. They have an AND command between them. So load the two dials in, and both of them there, and we get a result on the screen. So now we have, well, them both set to 0, which is 0, 0, 0, 0, and they're all zeros. So the result is understandably 0. If I switch it to 1, the other one's 0, so 1 and 0, the result is 0. Obviously, they're not both the same. I switch it to 1. They're both 1. 1 and 1 is true, gives a result of 1. Now, logically, in terms of a logic circuit, any non-zero value will come as a true and 0 will be a false. So if I switch this to 2 and that to 1, as a logic AND, it should give a true. But as a bitwise AND, if I switch that to 2, we go back to 0. Because what we're doing here is we're comparing each of the bits. So 2 is 1 and 0, and 1 is 0 and 1. So when you compare the first two digits there, you've got a 1 and a 0. That's a false. They're not both set. When you compare the second two digits, which is a 0 and a 1, they're both not set. So that is also a false. So that's the reading we get there. Now, if I switch this up to a 3, increase to 3, we now get a result of 1. So we're comparing 3 and 1. Now, 3 has a value of, or binary value of 1, 1. 1 has a binary value of 0, 1. So when you compare the first two bits, you get a 1 and a 0, which is a 0. And you compare the second two bits, you get a 1 and a 1, which is a true, gives us a 1. So the end result is 0, 1, or 1 in binary, as we squishy humans like to do it. So if I switch that up to 2, we're now comparing 1, 1 with 1, 0. So the end result is 1, 0, which is 2. Still with me? So I switch it up to 4, which is 1, 0, 0, compared to 0, 1, 0 is 0 because none of the bits have matching values. So that's where we've got to be careful using it in a logic sense. So if you're comparing things like a countdown timer for your storm against something else, if you say that your storm countdown is non-zero, which is a true, and something else is non-zero, which is a true, therefore something happens. It might not, because if you get the wrong values in there, or right values, depending on what you're trying to do, it may give you a comparator there. So it's always important, if you want to check a number which is not either a 1 or a 0, use a set command to set it. Say, is that not equal to 0? Which will give you a true or a false with a 1 or a 0. And then you can safely compare it with an AND value, because the AND is a bitwise comparator. But not what we've got to worry about at the moment. Let's just talk about how we're going to extract that. We're going to use the AND command to compare a value which will compare bits in itself. So if I set this to, say, if I set that to 7, which is a value of 1, 1, 1, 1, 1, or however many, and I can now set this to whatever value I like, and because it matches all of those bits, that value will come out until I go too high. If I go to 8, which is a bit we're not looking at, everything else goes to 0 from there, unless you go to 9, which reactivates the 1 bit. So that's what we're going to be using. So that's called a bit mask. There's probably another thing there. We probably need to talk a bit about hexadecimal. Now, hexadecimal is a base 16 numbering system. So we use the digits 0 through 9 and the letters A through E. Now, A through F. Yeah, that'll probably do better. So with F being 15, once you get to the 16th value there, you go back to 10. Now, we use that just as an easier way of representing binary values, because when we're sort of saying there, I set that to 7, which is 1, 1, 1, 1. It is 7 ones. Yeah. Anyway, it's a number of ones there, so it gets confusing reading all the ones in it. So you represent it as a hexadecimal code. You've probably seen them before written down with color values and things like that when you're trying to copy them in. It is a bunch of numbers and letters with a maximum letter of F. Now these ones are easier to read because each one of those letters represents 4 bits. A mask that would have been, so just to get the first, just to set the first 8 bits in binary would just be 1, 1, 1, 1, 1, 1, 1, 1, lost count, or it can just be FF. And so once again, if you want to get the second 8 bits, because some of these ones there, we do want the second 8 bits, so that would just be FF00. And we set all those bits and we can just pull out that value. Okay, so that you will probably be representing things in hexadecimal just to make them a little bit easier to read. You will see it done, but yeah, it can be confusing, but the more you use it, the more it makes sense. And yes, we do have hex values in here to help you with that there. So it does say it's just a $sign followed by a number of numbers and letters that it will put in as a hexadecimal code. So if we put in, if I just put in a hexadecimal of F, it should be 15. And I just move into R0 dollar F. That should be 15. Export, switch you on, and we get 15. So F is 255. So that's an 8-bit value, 255 with all the bits set. It's easy to remember that because as things start getting bigger, so if you want a number which is the second, which is the 16 bits over here and not the first 16 digits there, you have to AND it with a value which is that. If you can figure that out and remember that easily, good luck to you. I'll stick with hexadecimal. Thank you very much. Now, we are back to where we were. So we've got this value that we have constructed. Boink. So we've got all of them. Now get rid of you. Now we have that, export, and we have this number there. All the values are in there. We now have to extract them. So as it was, if we want to get that hash value back, well, let's start with an easier one there. So if we just want to get the opcode back, which was 2. So all I have to do is make our mask. So we can just AND it against the mask. So AND the R0, I'll set it to another one. We'll pull out the opcode R1 by saying AND with the value we've got and our mask, which was the 16 bits, which was the 16 bits that we put, 8 bits that we put at the start. So we say confirm on that one. If we export that, we should have 2 come back to us. Oh, and maybe display R1 might help too. Export. And we've got our opcode back. Now, if we want to get our number back, I can just set my code to the second 8 bits. F1. So it was the next 8 bits. So double F, they're 4 bits each, remember. So we want these 8 bits and not the first 8 bits. And we say confirm, export, and hang on a minute, that's not the 5 we want. That's because we have got the 5 and it is still shifted over. So I have to shift right logically, shift it back by 8 bits. Confirm, export that one, and we've now got a 5 back. Okay. Once again, to get our hash code back again, we need to, once again, we want to take, now this one is a 16-bit value. I think it's a 32-bit value. So we shall need to make up our mask with, that's 8, 16, 1, 2, 3, 4, 32 bits, and skip the first 16 bits. Now in binary, that would just be a nightmare number to go to, so that's why we're using hexadecimal here. And of course, we need to shift right logically, but the 16 bits to bring it back to where we start. So if we export that, we should have our value we want there, 1509191, which is what we've got there, as you can tell by the tooltip. So that is our bit masking. Now, so there's a number of ways you can do it. It doesn't really matter which way they end up in the same spot. Because instead of doing that, you could shift it first and then map it. Because if I want to get, say, so if I shift it first, if I shift logically right, now all the numbers that are below just fall off. They're replaced with zeros at the top end. So that brings that back to the first bit there. Then I just have to map anything else off it. So we just want 32 bits. So we're just causing 8 Fs there, which should be 111111 by 32 times. And we end that with that value and it should give us what we're looking for. Experts, so it should still be that's not the same. Let's try that. There we go. Right. So we've shifted it back to the right and then just chopped off the bottom 32 bits, which is what we want. It doesn't matter which way you go. Just do whichever one makes sense to you. They both end up in the same place anyway. So that is our bit mapping. That's what we need to actually work with these machines here, because it has been, it's in the logic sorter, it is in the printers, it is now been extended to the satellite dish, which is up there somewhere. The medium satellite dish now has a stack as well, and it operates on the same values there. So that is the basics of how we're going to map things there. I say be careful with your program with the AND command, because it is a logic comparator, and that's what a bitwise comparator does. So yeah, so that's basically the in and out of that. If you can understand all of that, you're becoming a programming genius there. So we can put values in, we can construct a value by just shifting your values and adding them together, and we can deconstruct it by using a bit mask. So hopefully that's helped and cleared things up. I've tried this a number of times and it's turned into complete gibberish. I hope I haven't just come out as complete gibberish again, but yeah, anyway, that is bit mapping and masking. I hope that's helped. But that's about all we got time for today. So until next time, happy building. See ya.